All right, we're continuing our discussion of phase changes in chapter 4. Specifically, we'll talk about the chemical potential, which is covering Atkins 4A and B today. The specific question I posed at the outset, or one of the specific questions, is what thermodynamic criteria describe equilibrium? The second law of thermodynamics tells us that delta G is going to be less than or equal to 0 for any spontaneous change. Systems will continue to evolve until G is a minimum and delta G is equal to 0. We have this natural equation for G, dG equals minus S dt plus V dP. And this suggests that changing pressure or temperature can impact G. That's certainly true. Changing pressure and temperature can impact B, but I want to try and convince you that, in fact, that's not enough. So, imagine this scenario. You're boiling a pot of water. It's at 100 degrees Celsius. And above it, I have air. Air at 1 atm, I should be specifically. If you let this sit long enough, probably a couple minutes, what happens? Right? Well, spontaneously, you will form liquid water at 100 degrees C plus steam, right? That is H2O gas. This is still at 1 atm, right? I would have air above it. And in this scenario, pressure and temperature haven't changed, right? 1 atm, 1 atm, 100 degrees C, 100 degrees C. Yet we all know that this will happen. So considering pressure and temperature is not enough. We need something else. And that something else that we need is the number of moles, the amount of stuff. Here's the idea. Substances have an intrinsic thermodynamic energy associated with them. And I can change G by changing the number of moles of a particular substance that's present. If the gas phase has a lower Gibbs energy than the liquid phase, I can lower the energy of the system by making more gas. In other words, right, you can sometimes lower the energy of the system by changing its composition. The constant that we're going to use to describe this is mu. Right? And this is called the chemical potential. It's a potential energy associated with a substance. Right? So delta G is equal to mu delta N. And I said here mu is a constant. Not really true, but don't worry about it yet at this point. Here's the rigorous definition of the chemical potential. It is the partial derivative of G with respect to N when PT and all the moles of everything else are held constant. As I just said, chemical potential describes a kind of potential energy, in this case, a thermodynamic free energy, which is associated with the composition of a system. And a system can sometimes lower its Gibbs energy by changing its composition.
I know that smells like that now. It's goat milk soap.
We just got some goat milk soap in our mailbox, and my wife is telling me that it's stinking up the house and the kitchen. Important things, just like chemical potential. All right. I can now answer for you this question, which was burning in your mind, I'm sure. What thermodynamic criteria describe equilibrium? Here's the answer. At equilibrium, the chemical potential of a substance is the same throughout the system, regardless of how many phases are present. If you're taking notes, write this into your notes and circle it. This is going to be our definition of equilibrium moving forward. At equilibrium, the chemical potential of a substance is the same throughout the system, regardless of how many phases are present. An important note here, unlike pressure, volume, delta G, we are almost never going to calculate U directly. You will have no cycle questions asking you to calculate delta mu. Instead, we use it as a vehicle to connect other variables when a system undergoes some change. I'm going to show you the most important example of that in the next video. And that, my friends, is called a tease. So I hope you'll watch it, and we'll see you then. Okay, thanks everybody. I wanted to try video editing, so thanks for humoring me. I wanted to give you two examples of how we can use chemical potential. And one thing that we need to recognize, or that's useful, is that for certain substances, the chemical potential is constant. Specifically for pure substances, things which cannot undergo a chemical change. In that case, the change in chemical potential is simply the molar Gibbs energy. And so all you have to do is take the natural equation for G, divide it by N, and you get an expression like this. du equals minus S molar dP plus Vm molar dP. And here's how you can start to think about this. If I can get my pen to work, which right now I can't. There we go. Let's imagine I made a plot of chemical potential versus temperature. This expression is telling me that the derivative of the chemical potential with respect to temperature when pressure is constant is minus S molar. Right, so it's related to the molar entropy of the substance. I also know that S molar of a solid is less than the molar entropy of a liquid, which is less entropic than a gas. Gases are our most entropic species, solids are our least. So if I interpret this now onto this plot, what I'll get are sort of three regions. There's one region associated with the solid, there's one region associated with the liquid, and one region associated with the gas. Solids are the least entropic, so they have the smallest slope. Liquids are in the middle, gases have the biggest slope. And what this plot is telling me is that at this temperature, right, low temperatures, solids are the least entropic and therefore have the lowest chemical potential. At some point, the chemical potential of the liquid will drop below it, and the system will spontaneously transition from a solid to a liquid. Okay, this temperature right here is the melting temperature. If I continue, at some point the gas becomes lower in chemical potential than the liquid, and it will vaporize. I wrote right on top of myself, but this explains the stability of phases. Here's another example, and this one's a little bit harder. Changes in transition temperature with pressure. So I'm going to make another plot like I had just done. Chemical potential versus temperature. Here's a solid, here's a liquid. If I think about changing the pressure, what this equation tells me is that the change in chemical potential is equal to the molar volume times the change in pressure, provided temperature is constant. And so if I think about increasing the pressure, the amount that the molar volume, sorry, the amount the chemical potential changes is proportional to the molar volume. For most substances, the molar volume of the liquid is greater than the molar volume of the solid. Solid is more dense. And so because this is bigger, what ends up happening is I get a big change in this one. This is VM, my pen isn't working, VM liquid delta P, and a much smaller change here. Right? This is going to go on and this is going to go on. So this change here is VM solid delta P. Because the molar volume of the solid is less than the molar volume of the liquid, this one increases more, and this is my new melting temperature. Okay. So originally it melted here. If I increase the pressure, what often happens is that the melting pressure increases. However, can you think of any substances for which the molar volume of the liquid is less than the molar volume of the solid? Right? Where the solid is less dense, right? And the liquid is more dense. The answer is water. And I'm not going to go all the way through it. If you want to, you could go through and sketch it out. But what you will find is the exact opposite happens. If this is true, the fusion temperature decreases with pressure, right? Rather than increasing here, it increases back this way. And this explains why the slope of the solid liquid phase boundary in the phase diagram of water is negative, right? Why does the melting temperature decrease with increasing pressure? Well, it's ultimately because the solid is less dense than the liquid, right? As almost always seems to be the case with water. All right, I hope you enjoyed that little post-credit scene, and I will see you next time for a discussion of Clausius-Clapeyron.